Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we are going to be combining a lot of the tricks we've learned over the last several lectures to combine a little bit of rotational spectroscopy with a little bit of vibrational spectroscopy. So one of the big things to remember is actually going to be to do with our selection rules. So when I have, say, an IR spectra, my molecule is essentially absorbing light to excite the vibrational frequency. However, it turns out that vibrational excitations have a lot more energy than rotational excitations. And as a result, when you're doing a vibrational excitation, one of the things that can happen is that a little bit of that energy can go into rotational motion. It's also possible for a little bit of that energy to actually come from rotational motion. So if you have a little bit too much energy in your light, pass it off to a rotational uh, mode. If you don't have quite enough to make ends meet, steal a little bit of energy from one of your rotational uh, modes. And this is actually going to cause a little bit of broadening of a vibrational spectra. However, it broadens in a way that tends to be kind of very unique in that we get sharp peaks. So this is what's called a fine spectra. And this fine spectra is actually going to embed a lot of information about our rotational spectra inside of our vibrational one. And it's composed of three main branches. So the first of which is going to be called the R branch. So this occurs at slightly higher wave numbers, which means slightly higher energies. So this occurs essentially when I have a vibrational excitation, a little bit of that extra energy goes into a rotational mode. So thus it requires a little bit more energy, a little bit higher wave number. We also have the P branch where I don't have quite enough energy to make ends meet. So in addition to absorbing light, I'm also going to steal a little bit of energy from my rotational mode and put it into my vibrational excitation. And then the last is doesn't occur most of the time, and it's called the Q branch. So this is where J doesn't change. So this is classically forbidden because it turns out um, whenever you absorb light, you need to change the angular momenta of the relevant molecule. So usually this is going to go into rotational modes. Sometimes you can actually, under select circumstances, you can actually generate a Q branch. And we'll talk about that in a bit. So what we're going to want to do is, first of all, kind of dive into the ideas of our energies. So we're going to be expressing all of our equations in terms of wave numbers. And so we're going to give a total energy for our for vibrational and rotational motion in what's called the vibrational rotational term, which we're going to here represent as S tilde. So this is going to be a combination of our vibrational energy and our rotational energy, which we've already essentially established. So we're going to start by ignoring any sort of complicating factors. So for the vibrational term, we're going to ignore any anharmonicity, and we're just going to use the energy equation from the harmonic oscillator. So this is given as the vibrational constant times the vibrational level plus 1/2. And then for the rotational term, we're going to ignore any centrifugal distortion. We're going to start by assuming we have a nice spherical or linear rotor, which will help keep our equations fairly straightforward. And here, B is going to represent our rotational constant, again, under a simple rigid rotor approximation. It is worth noting you can extend this to include higher order terms, but it's going to kind of complicate the math. And we want to kind of focus here on the key elements. So it is worth noting this just gives us our energy, and this is spectroscopy. So what we're going to care about is energy differences. And we're going to solve these for each of the branches individually. So for our branch, we're exciting the system from a low vibrational state to an excited vibrational state. And when we do this, we're also going to excite our rotational state as well. So we go from, say, V of 0, J of 0 to V of 0, J of 1, and J of 1 to J of 2, J of 2 to J of 3, and so on and so forth. And it is worth noting that this diagram is actually kind of underselling it. The separation between vibrational levels is much greater than the separation in rotational levels. So this top level should probably actually be somewhere here at the top of the page, and that might be about right. Now, for this R branch, what we can then do is say, if I start at a state of V and J, then I'm going to a state of excited state of V plus 1 and J plus 1. And again, this should be in the most general case. So then what we can do is, using our energies for our vibrational and rotational states, we can go ahead and plug that in. And so what we have is, we can pull out our vibrational constant, and what we end up having here is the difference in between my ending vibrational state and my starting vibrational state, and the same thing with rotationals. Now, for the vibrational state, this is actually really nice and pretty because, well, congratulations, the V's cancel, all we're left with is 1. So we just have the rotational, or the vibrational constant. And for the rotational level, again, we have to distribute the system, do some cancellation. We're left with twice the rotational constant times J plus 1. I want to make note that this should look fairly simple and familiar, because this was the answer to our harmonic oscillator. This was the answer to our rigid rotor. So no matter what your starting vibrational state is, we shouldn't see any influence on the absorption energy. However, depending on what J state we started in, we are going to see a slight difference. And as a result, what we tend to see is that we're going to have many discrete peaks, with the highest peaks corresponding to a high J, the lowest peaks the lowest peak typically corresponding to a J of 0. And as you can see here from amplitudes, we expect the highest amplitude to occur somewhere in the middle, because of issues of degeneracy tending to favor these middle rotational states. And again, we're going to see this signal shift depending on J, high frequency, low J, low frequency. And again, frequency and wave numbers will be proportional in nature. However, we also have our Q branch. So this is the one where the rotational state does not change. So this is classically forbidden. However, you will occasionally see a Q branch appear if there is an electronic term which can actually absorb some angular momentum. This is uncommon, but not unheard of. However, when most systems you work with are typically going to have no appearance of a Q branch. And this leaves us with the last of the three, which is the P branch. So we're going to examine this kind of in a similar fashion as the R branch. Biggest difference here is, while V is increasing, J will be decreasing. So our excited state is going to be V plus 1 and J minus 1. So our vibrational term is going to be the same as it was for the R branch. Here, well, our difference becomes a little bit more kind of fun, as our excited state now has a energy provided by J times J minus 1. Now, this one's actually a little easier to do, but it still requires some distribution. However, through distribution and simplification, what we find is the rotational term is going to be dependent as twice the rotational constant times the rotational level. So one of the big differences, though, from the spectra is, on the R branch, your lowest peak corresponded to a J of 0. Here, our lowest value is going to correspond to a J of 1 because we have, in order to drop rotational levels, I have to be in an excited rotational level. However, keeping this in mind, we're going to see very similar factors from the R branch, just reversed. We're going to see lower and lower frequencies as I increase my value of J. And one of the ways to think about this is I'm able to steal more and more energy from my rotational term. So I need a little bit less energy to come directly from the light because, again, lower frequency, lower wave number, lower energy. Now, this is going to help. This helps explain the characteristic structure of a rotational vibrational spectra, which you will have a chance to play around with in lab. This is the famous Hickel-Dickel lab. However, one of the key features that we like to kind of do with these spectra is that it's actually possible to combine the information from our R branch and our P branch to get a lot of information about our rotational constant. So if you want to know a lot about our rotational motion, we don't actually have to have a microwave spec. We can do this with an IR spec as long as the system's relatively simple. So what we can do is take the difference in between the R branch as it goes from the J minus 1 to the J state, and the P branch as it goes from the J plus 1 to the P state. So essentially, both of these states end at the same point. And what this means is that I can get the I can use this to get the difference in between the rotational energies of my ground state. And again, this can be provided as twice the rotational constant times J plus 1/2. Now, what's really nice about this is that these values can essentially be calculated and then plotted versus J to generate a linear relationship. And it turns out physical chemists love themselves a good linear relationship. So you should be able to get an intercept of our rotational constant and a slope of twice our rotational constant. So this is essentially a good way to A, double check your data, but also B, obtain your rotational constant. Not to mention, you can get your vibrational constant simply by then subtracting out your rotational constant and then getting the vibrational values. However, it is worth emphasizing this method does ignore any effects of centrifugal distortion and anharmonicity. So it doesn't acknowledge that we're using a Morse potential, and it doesn't acknowledge that the system stretches out. And it is worth noting that there are going to be more advanced equations that can be used to model these two effects. And this is something that we will be doing in lab. However, that brings us to the end of our introduction to basic quantum mechanics. So next time, we're going to actually get into some more fun chemistry as we get into atomic structure. Till then, take care.